Hello, everyone. Welcome back to Math 301 Combinatorics. And this week we're starting Chapter 5, which is all about proof techniques in combinatorics. This is a really valuable and useful chapter about why proofs are so important for mathematicians and a little bit about the history of proofs in combinatorics and in my research area, number theory, which has a really interesting history of proofs. So the way that a lot of mathematicians think about proofs is as a living language, a way of connecting the thoughts of people from ancient times to the thoughts of people today. And another way of thinking about it is that we not only want to understand what is true, we also want to understand why it's true and to be able to communicate why something is true. So let's take a look at section 5.1, which is a introduction to proofs. And I want to tell you about Ramanujan's constant. So this number e is approximately 2.71, and this number pi is approximately 3.14, and the square root of 163 is a little less than 13. And if you raise e to the pi squared of 163, you get this number, huge number, but notice that after the decimal point, it has lots of nines. And so it is extremely close to this whole integer plus 1, so that the ending digit is 4. And so when you look at this, then you might think, of course, this is just a small calculational error, and this is actually a whole integer. And Gardner sort of made a joke that Ramanujan had conjectured that this number was an integer. That was actually an April Fool's joke. And it turns out it's nowhere close to being, well, it's close to being an integer, but it is essentially different from an integer because it's not even a fraction. It's a transcendental number. So it doesn't even satisfy an algebraic relationship. Like the square root of 163 has a nice property that its square is an integer. This number is transcendental in that you can't do anything algebraic to this number and end up with an integer. So I guess I brought this up in this section because it gets you to start thinking, like, how much evidence do you need to convince yourself? How much accuracy do you need to convince yourself whether something is true or not? And that's at the heart of proofs. So let's look at another example from history. So, and this is the topic of what are called Fermat primes. So Fermat was a famous mathematician from the 1600s in France, and he looked at numbers. Let's call them. He picked a number a, and then he looked at a number fa, which is of the form 2 raised to the power 2 to the a plus 1. Okay, so this number, let's just compute a few of these. So when a is 0, you get 2 to the 0, so that's 2 to the first power plus 1, you get 3. When a is 1, you get 2 squared plus 1, that's 5. You can continue, so when a is 2, you get 17. When a is 3, you get 257. And when a is 4, you get 65537. And what Fermat noticed is that all of these numbers are primes. And this was fascinating to him because people at that time were trying to find a formula to produce prime numbers. Of course, primes are, except 2, are all odd, so this is a good place to start. And so he found that by looking at numbers of this form, he had produced prime numbers. And so he was hoping that he was hoping, so this is the hope, is that fa is always prime. But it turned out that was wrong. So Euler, a while later, showed that when A is 5, then F5 is some huge number, but what's important about it is that it factors as 641 times 6700417. And the important thing is that this number factors, and so it's not prime. And even to this day, people don't know whether there are any other primes that will show up as the number F, as the number FA for some A. These primes, this formula is still used to produce large primes, because even if some number like F5 is not prime, it might have a big prime factor. And so that's a useful way of finding big primes. But in general, people don't know how many primes are going to show up. How likely is it that FA is going to be a prime number or not? So, so here you might say that this wasn't very much evidence to base a hope or a conjecture on. I mean, here this was only 5 different possibilities for A, which showed that where FA was a prime. So maybe that wasn't too much evidence, but sort of the question is how much evidence is enough to make you believe whether something is true or not. Let me just briefly tell you about Fermat's last theorem. I'm very fond of this theorem because it was proved right when I was in graduate school, and it gave me this huge confidence that people were going to prove all the big theorems in short order. But in fact, it's probably the biggest theorem that's been proved in number theory in my lifetime. So the idea is that if x, y, and z are integers, and if n is greater than or equal to 3, which is an integer, then x to the n plus y to the n equals z to the n is only possible if one of the 3 is 0, which we can summarize by saying is if x, y, z is 0. Okay, so if you take n to be 2, then there are lots of pairs, triples of integers where x squared plus y squared equals z squared. Those are all the Pythagorean triples. For instance, 3 squared plus 4 squared equals 5 squared. But once you get up to the number 3, then it is impossible for x cubed plus y cubed to equal z cubed if x, y, and z are integers, unless one of them is 0. So you can always take y to be 0, for example, and then just set x to equal z, or you can take y to be negative x and z to be 0. So there's some trivial solutions where x, y, z equals 0. But if you want a non-trivial solution, then there aren't any. So Fermat conjectured this in the 1600s, and it took 300 years to prove. Wiles and then Taylor-Wiles proved this theorem, and the history is quite fascinating if you want to watch. There's some documentaries about it. Okay, so let me just say a little bit about some proofs that came out that people were initially not happy with, but now are accepting, and another proof that people think is not a proof. So one is what's called the 4-color theorem. And the idea is that if you take any map, and we have to be a little careful of what we mean by a map. So each country has to be connected. We can't have different parts here and there. Then it turns out that you can always color this map with 4 different colors. So let's try to do that. So for example, I'm going to if I make this part red, then actually I can't make any other of these countries red, but I could make some of them green. So this one could be green. Oh, and I needed to say that on this map, you can never put, if two countries share a border, they can't have the same color. So I could make this one blue. And then we get to this country, and it can't be red or green or blue because it shares a border with all those different colors. So that's why you need the fourth color, maybe purple. So this is an example of coloring a map with 4 colors. And the statement was that under some very mild conditions on what the countries look like, every map can be colored with 4 colors, so that no countries that share a border have the same color. So this is really a theorem in topology and combinatorics, and people really struggled to prove it. It was finally proven in 1976 by Apple and Haken, and it was one of the very first proofs that used a computer to prove it. So they first used mathematical proof reasoning to categorize all possible maps into different types, and then they used a computer to exhaustively check all of these cases. And at first people were very skeptical about this because computers were very new at that time, and nobody was really quite sure whether we could be fully convinced that the computer had checked all the cases and was fully accurate. But over time, and as computers have improved, this proof has been re-verified, and now people feel very confident about it. There's a different proof called also one in number theory, called the ABC conjecture. And this, well, maybe I'll tell you about two things. One was the ABC conjecture. Another one was the Perlman's conjecture. Sorry, excuse me, the Poincaré conjecture. So these are 2 completely different conjectures. One of them is in number theory, and the Poincaré conjecture, I'd say it's in differential geometry. And the Poincaré conjecture, I forget when this was, maybe about 15 years ago, or no, maybe a little longer than that, like 25 years ago. Somebody came out of the blue and said, I've proved the Poincaré conjecture. And this person was not working at any university. He was working by himself in a small house in Russia, and people were initially a little skeptical, but it turned out that after a lot of the experts had read through this proof of the Poincaré conjecture, that they really agreed. This is proved, and this person had found new insights and new theories that were enough to extend the boundary of knowledge of what mathematicians knew. So in contrast with the ABC conjecture, a very well-known mathematician claimed to have proved this conjecture, and there were many conferences about it, where he and some of his graduate students would try to explain the proof of the conjecture. And it was 1,000 pages of text, and so it took a very long time for even just to try to read through them and understand what was going on and see whether this proof of this conjecture was there. And finally, a few other very well-known mathematicians went online and said, we don't think this is right, and in fact, we think the mistake is here. And so right now, in fact, people don't think the ABC conjecture has been proved, although there's some disagreement about that. So once we get to these very big theorems in in mathematics, checking whether a proof is correct or not can be very difficult. But I want to end today by just telling you one example of a short proof, one of the oldest known types of proof, which is a proof by contradiction. And so the idea with the proof by contradiction is that you look at what you're trying to prove. So this is what you know. This is what you're trying to prove. Okay, we're trying to build a bridge from what we know to what we're trying to prove. And so what we're going to do instead is, so this is our goal. We're going to assume the negation of our goal. So we're going to assume the opposite. So we're going to assume that the opposite of our goal, the opposite is sort of the negation of our goal, is true. And so, and then we're going to deduce things logically in order to show that we get to some kind of completely bogus conclusion. And so if we're going to assume that our goal is false, and then we're going to try to deduce from that some completely bizarre and obviously false fact. So, and the only way that the logic of this can break down is if our goal was actually true. Okay, so let's do an example of that. We're going to prove, so in this case, our goal is going to be to say that the square root of 3 is not a fraction. And so we're going to assume the opposite. We're going to assume the square root of 3 is a fraction. And then we're going to try to contradict ourselves. Okay, so if square root of 3 is a fraction, then we can write the square root of 3 as looking like a over b, where a and b are integers, and b can't be 0. There are a lot of different ways to write down the same fraction. For example, 1/2 is the same as 2/4, is the same as 3/6. And so we say without loss of generality, we can write a over b is in lowest terms. What that means is that there are no factors that a and b have in common. So the greatest common divisor of a and b is 1. Okay, and then we're going to square both sides. So the square root of 3 squared is 3, and a over b squared is a squared over b squared. And we can simplify that to write this as 3b squared equals a squared. Now 3 divides the left-hand side. So 3 divides a squared. And 3 is a prime number. So if a prime number divides a squared, then it has to divide, when you factor a squared as a times a, this 3 has to divide either the first term or the second. So we get that 3 divides a. Once 3 divides a, we can write a as being 3 times some other integer, like a1, and then we can substitute that into the equation. That gives us that 3b squared is 9a1 squared. So I want to keep this all on one slide. Oh, this is not a good idea to keep this on one slide. Running out of space. Okay, so what we can do is we're going to cancel the 3 from both sides, and we're left with b squared is 3a1 squared. But then 3 divides the right-hand side, so 3 divides b squared. This is the symbol for divides. 3 divides b squared. And by the same reasoning as above, that shows that 3 divides b. But then we've seen that a and b have something in common. They're both divisible by 3. So there's no way that their GCD can be 1 if they're both divisible by 3. And so we've just contradicted this step in the proof. And so that shows that, that our assumption is wrong. All right, so at the end of chapter 5, we're going to build on proofs by contradiction in order to study the pigeonhole principle. But before we do that, we're going to look at proofs by induction and proofs using bijections. Okay, see you next time.